Hello all. I'm Rijumon Nandy, and my work is on the ancient topography and climate of southwestern Montana, and I'm using volcanic glass hydrogen isotopes to study this phenomenon. My work largely evolves around understanding the elevation history of mountain belts, whether it has increased or decreased in elevation, has profound effects on what are the tectonic processes that are controlling that elevation change, and helps us know in much detail about the tectonic plates involved in the creation of the mountain belt. For my study, I am working on the uh, North American Cordillera, which runs across the western US, all the way from Alaska to Mexico. And my work is largely focused on this narrow basin in southwestern Montana, known as the Sage Creek Basin. We are mainly looking at the history from about 50 to about 20 million years ago, and we have chosen this basin similarly because it has a large, thick sedimentary layers running all across the period of our significance. So our motivation to study this came from a recent paper in 2021 by Lee et al., who suggested that there was an uplift in the region or in the North American Cordillera during the early Oligocene, which is about 32 million years ago. It was the first of its kind paper to suggest that, and also had a very unique mechanism linked to it. So in our study, we are trying to test this hypothesis or test this early Oligocene uplift theory in the North American Cordillera. Alongside that, we are also assessing the climate of the North American Cordillera during the middle to late Eocene period. So for our study, like I said before, we are using volcanic class hydrogen isotopes. Volcanic class, it very efficiently preserves the precipitation waters from ancient times. Precipitation waters have obviously H2O, so hydrogen, and hydrogen has two isotopes, one heavier, which is D or deuterium, and one lighter, which is H or hydrogen. These are very efficient to understand elevation changes. At increased elevation changes would lead to decreasing amount of the heavier isotopes in the precipitation waters. And so the del D values, which you're signifying as the for the isotopic ratio over here, would progressively decrease if there is an uplift. So that is the best way our data can show an uplift or can suggest an uplift during a period if there is a very sharp decrease in the del D values uh, during a small period of time. So coming to our results, uh, we separated the volcanic glass by the standard procedures, and then we sent them for analysis, del D analysis. Coming to our results, the blue and green dots are the results of Lee et al. And this is the specific oligocene uplift that he was suggesting. However, a more expansive data set in this region from our study suggests that there is no such major shift during the early Oligocene period. However, our data set, the red dots, also suggest, just looking at the baseline, there is about a 6 per mil isotopic shift in the positive direction across the regional unconformity, which is from the middle to late Eocene period. As for to further elaborate on our results, the results till now suggest that this increased shift is probably due to a global cooling period, which is observed from the benthic foraminifera del 18O values. And we can see there is a global gradual cooling trend up till the Eocene, late Eocene, and a drastic cooling trend in the Eocene Oligocene boundary. So this possibly this increase in the hydrogen value is reflected is a result of the source waters being uh, uh, isotopically changed due to a cooler climate. We So our basic idea of the data is to understand the isotopic changes and see if it is related to uplift. There's still a lot of work to be done in this data, and I uh, hope I can bring even more results in the later uh, editions of Discover. There is a lot of work to be done on this as well. So yeah, thank you.